Hello. In this simulation, we're going to calculate the force on a wire. This simulation shows the setup as previously discussed, a short conducting wire held at a fixed height inside the yoke, and a current is passing towards you along this wire. Let's select vectors to see vector arrows showing the size and direction of the flux density B, the current I, the upward force F on the wire. If the length of the wire is L, then these quantities are related by the equation F is equal to BIL. The lower small diagram shows an overhead view of the wire and the flux density vector arrow of value B. At the moment, the flux density is perpendicular to the wire. Let's drag the wire angle slider one notch to the left to rotate the wire so that it is at 60 degrees to the magnetic field lines. What happens? Yes, the force registered by the balance is reduced from a mass equivalent of 0.6 gram to 0.52 grams, and the upward force vector arrow gets shorter. Look at the lower small diagram. The flux density vector B still points from one magnet to the other. The upward force on the wire is due to the flux density component B sine theta acting perpendicular to the wire, where theta is the marked angle between the lines of force and the wire. This was originally 90 degrees and now is 60 degrees. Let's compare the constant length of the B vector in the lower small diagram with the length of the component perpendicular to the wire. The original force, BIL, of value equivalent to a mass change on the balance of 0.6 gram has become BIL sine 60, which is equal to 0.52 grams. You can check this by multiplying 0.60 by sine 60. Now let's change the wire angle to 30 degrees and look at the balance reading and the length of the component of B perpendicular to the wire. Calculate 0.60 sine 30. What do you notice? Yes, the balance reading and the calculated value are the same, which has a value of 0.30 grams. Finally, let's change the angle to 0 degrees. Check the balance reading and calculate 0.6 multiplied by sine 0 to see if the formula F equal to BIL sine theta still applies. Yes, since sine 0 is equal to 0, the force here gives a 0 mass equivalent. That's correct. Good job.